Hello everybody, we're PokerCam. To monitor card games today, most professional casinos place cameras around a table and manually review the footage to identify cheating or card counting. However, manually reviewing this game footage is a time-consuming, expensive process that is difficult to scale. Tournament spectators may also benefit from this bird's-eye view of the card game when viewing live games. That's why we created PokerCam. Our standalone card shoe is a drop-in replacement for existing systems, and it adds an automatic imaging and machine learning system to classify cards and update a web display in real time with the game state. PokerCam directly replaces existing card shoes used in casinos, so there is no need to train new dealers in new technologies. This allows spectators, commentators, and casino workers to visualize each game in real time without the overhead of manually reviewing footage. Our system is cheap to produce and easy to scale for large casinos hosting many games in parallel.
Here's an example of two players and a dealer sitting down to play a game of Texas Hold'em using the PokerCam system. The dealer puts in the number of players and selects the game. The dealer can then add custom names for each of the players. Once everything is set up, all that's left to do is start playing. Within a fraction of a second, the PokerCam system will correctly identify the cards dealt to each of the players. PokerCam knows the rules of each game. For example, in Texas Hold'em, our system knows which cards are for each player and which cards are the community cards. It even recognizes rules in professional poker, such as card burning, where a card before each of the community deals is not used. PokerCam also supports other games, such as blackjack and war. Let's now talk a bit about how PokerCam works. The brain of PokerCam is an NVIDIA Jetson Nano. This onboard computer controls the camera system, does the image processing, and sends the data to our custom web app. The Jetson Nano is battery-powered and can last for hours on a single charge. It connects wirelessly to the internet, so no extra cables are required on the casino table, ensuring that your tournament can keep running with minimal interruptions. Using our in-house custom-designed PCB, PokerCam employs infrared reflectometry to accurately identify which cards are being dealt. LEDs illuminate the face of the card, which assures quality images are captured. This then triggers our camera system, which takes a picture of the card as it slides out of the shoe. The whole system is then housed in a custom laser-cut enclosure. Once PokerCam images a card, it runs the image through a convolutional neural network to classify the card's suit and rank. The Jetson Nano wirelessly sends this classification result to the web app, which immediately updates the game state for viewers. PokerCam performs this entire process in less than a fifth of a second to provide viewers with up-to-date information about the state of the game.
Here is a demonstration of PokerCam's usage and latency. We deal the first few cards of a new deck in new deck order. The command line on the left shows verbose output and the camera's capture. The web app on the right is set for a two-player game of war. We highlight the short latency between the dealer retrieving the card and the graphic updating on the web app. Here is an example black and white capture from the camera after cropping and decimation. The shadow on the right is caused by the angle of the LEDs pointed at the card. The horizontal blur is motion blur due to the card's horizontal movement as it is dealt. The camera captured this photo at 60 frames per second, decimated the image by 4 times in both dimensions, cropped it to the center, and normalized the image with the training dataset's mean and variance. The NVIDIA Jetson Nano runs this image through multiple convolutional and fully connected layers to predict the card's rank and suit. After the first convolutional layer, the network outputs these activations. Note how these images highlight the edges around the rank and suit. The network finishes the forward pass to produce the following probability distributions. These example distributions show almost 100% certainty for the correct classification, a 9 of diamonds.
I'm now going to talk about the web application, which is a Python Flask application. It contains HTML and JavaScript on the front end and Python on the back end, which consists of game logic about which cards correspond to which players and if a player has won or lost. Our application receives an HTTP post request corresponding to the card classification and then routes that card classification to a player based off of the game logic. Our application is stored on AWS using the EC2 web service, which allows for data replication for high availability and fault tolerance. It's also scalable in the case there's increased traffic from audience viewers and commentators. We utilize PyMongo as a module for interfacing with MongoDB. MongoDB contains all our data about the game state, which players have which cards. The dealing has already been organized, and if a player has won or lost. MongoDB has sharding clusters to replicate data across nodes, so it's also great for high availability and fault tolerance. One of the challenges we ran into was reducing the amount of latency between RESTful API requests and the web app updating. In order to make this process faster, we maintained a fixed connection to the MongoDB database instead of making a new network connection every time a query needed to be performed. We also implemented asynchronous JavaScript AJAX calls to continually get the most recent data from the MongoDB database. I'll now talk a little bit about the edit card functionality over here. So if a card has been misclassified, for example, if the street of spades needs to be an 8 of diamonds, you can type in 8 diamonds, player 3. Looks like it's card number 2. I click edit. It's not working. Okay, I think I need to put in the password. I'm not going to say what it is, and click edit. And there you can see it gets edited properly. So the point of the password is to ensure that random audience viewers are not able to make edits to the web page. We want to make sure only verified individuals like commentators and tournament judges are able to actually change information on the web app. And this is for the security of the web app and to ensure the integrity of the information displayed.
We chose to capture black and white photos to improve processing time and reduce costs of future iterations of PokerCam. Color information in RGB captures may improve discrimination between red and black suits. However, the convolutional neural network achieved almost perfect suit accuracy with black and white images, so the RGB color space was not worth the added complexity. Since this system exclusively operates on black and white images, future iterations of PokerCam may include a monochromatic sensor to reduce the hardware cost. We settled on a convolutional neural network to classify images. Compared to support vector machines, the neural network outperformed SVMs on a real dataset. The neural network is robust to small translations on the image plane, so PokerCam functions consistently across different dealers who pull the cards at a slightly different angle. Paired with a 60 Hz camera, PokerCam's convolutional neural network accurately classifies cards despite any motion blur caused by dealers rapidly pulling cards.
For the web application framework, we're using Flask, which is lighter and more flexible than Django. Django is more powerful, it has more built-in modules and functionality, but we're using Flask because it gives us more control over all the technical details of our web application to best minimize latency. Instead of using SQL, another trade-off is using MongoDB, which is a more flexible database program, and this is better for our needs, as if we need to make changes to our data format in the future, we'll be able to do so, unlike with SQL, which has a fixed data format.
PokerCam requires 98% classification accuracy to appropriately track the game state. This near-perfect accuracy is achievable through consistent image poses and lighting. To test the classification accuracy, we imaged many decks of Bicycle Standard card decks and split those images into approximately 3,500 training images, 500 validation images, and 1,000 testing images. Our convolutional neural network achieved 97.9% test accuracy on the fixed test set of unseen images. This corresponds to approximately 1 misclassification per deck of 52 cards. This error rate allows future iterations of PokerCam to perform error detection by identifying the 2 cards with identical labels and highlighting them as possible misclassifications. PokerCam also requires there to be 0 false triggers. Any false trigger would mess up the dealing order for future cards. To test PokerCam's latency, classification accuracy, and trigger accuracy in a real-world environment, we manually dealt 432 cards and recorded latency and accuracy statistics. PokerCam achieved an average latency of 0.17 seconds and 97.7% classification accuracy without any false triggers. This meets our latency requirement and false trigger requirement and falls short of the accuracy requirement by just 0.3% in real-world conditions.
Thank you so much for watching. We'd like to give a special thank you to our faculty advisor, Professor Feder, as well as our TA Ryan for all their help and support throughout the last several months.